Cable bracing is required for utility poles primarily under three conditions. Firstly, when a pole is unable to withstand the lateral loads it is subjected to. Secondly, when a pole is damaged or weakened. Thirdly, to increase safety and reliability in specific high-risk areas. Let's delve into each of these scenarios in detail. When a pole cannot withstand lateral loads, this is a critical situation that demands immediate attention. Lateral loads refer to forces that act perpendicular to the axis of the pole, essentially pushing it sideways. Several factors can contribute to a pole's inability to withstand these loads. One major factor is high wind loads. Wind exerts significant pressure on the pole and any equipment attached to it, such as conductors and transformers. The force of the wind increases exponentially with wind speed, so even moderate winds can pose a considerable threat. The design of utility poles must account for expected wind loads in the region as dictated by engineering standards and local building codes. These standards typically specify the maximum wind speed that poles must withstand, along with safety factors to ensure structural integrity. Ice loading is another significant factor. In regions prone to freezing rain or snow, ice accumulation can add substantial weight to the pole and conductors. This added weight not only increases the vertical load on the pole but also significantly increases the lateral load as the ice coating catches the wind. The weight of ice can be surprisingly high. A single inch of radial ice can add several pounds per foot of conductor length. The combined effect of weight and wind pressure on ice-up conductors can easily exceed the pole's capacity, leading to bending, cracking, or even complete failure. Heavy conductor loading also contributes to lateral loads. Conductors, the wires that carry electricity, exert a constant tension on the poles. This tension is necessary to maintain proper wire spacing and prevent sagging, but it also creates a lateral force on the poles, especially at angles and curves in the power line. The heavier the conductors, the greater the tension and the greater the lateral force. Older poles may have been designed for lighter conductors, and upgrading to heavier conductors without reinforcing the poles can lead to structural problems. Uneven ground conditions can also compromise a pole's ability to withstand lateral loads. If the ground around the pole is unstable or has poor soil-bearing capacity, the pole may lean or shift under load. This is especially problematic in areas with soft soil, high water tables, or frequent freeze-thaw cycles. Proper pole installation involves ensuring adequate soil compaction and using appropriate backfill materials to provide a stable foundation. Proximity to other structures can create complex wind patterns that increase lateral loads. Buildings, trees, and other obstructions can deflect wind, creating areas of increased wind speed and turbulence around the pole. These localized wind gusts can exert unexpected forces on the pole, exceeding the design limits. In densely populated areas, careful consideration must be given to the placement of poles relative to surrounding structures to minimize these effects. The second major reason for cable bracing is when a pole is damaged or weakened. Damage can occur due to a variety of factors, including vehicle collisions, storms, woodpecker damage, rot, and corrosion. Even seemingly minor damage can significantly reduce a pole's structural integrity. Vehicle collisions are a common cause of pole damage, particularly along roadways. A direct hit from a car or truck can crack, splinter, or even shear off a pole. Even a glancing blow can weaken the pole, making it more susceptible to failure under normal loads. After a vehicle collision, a thorough inspection is essential to assess the extent of the damage and determine whether cable bracing or pole replacement is necessary. Storms can cause significant damage to poles through high winds, lightning strikes, and falling trees or branches. Wind can snap poles directly, while lightning strikes can cause internal damage that weakens the wood. Falling trees and branches can exert tremendous force on poles and conductors, leading to breakage or displacement. Regular inspections after major storms are crucial to identify and repair damaged poles. Woodpeckers can cause extensive damage to wooden poles by drilling holes for nests and food. These holes weaken the pole, making it more vulnerable to wind and ice loads. Woodpecker damage is particularly common in areas with large woodpecker populations. Preventative measures such as wrapping poles with protective materials can help deter woodpeckers. Rot is a common problem in older wooden poles, particularly at the ground line where moisture and oxygen are readily available. Washing wood loses its strength and can eventually lead to pole failure. Regular inspections with probing tools can help detect rot before it becomes a serious problem. Treatment with preservatives can slow the progression of rot and extend the life of the pole. Corrosion is a major concern for metal poles and hardware. Exposure to moisture, salt, and pollutants can cause rust and corrosion, weakening the metal and reducing its load carrying capacity. Regular inspections and maintenance, including cleaning and painting, are essential to prevent corrosion. Cable bracing can provide additional support to a damaged or weakened pole, helping to prevent it from collapsing. The bracing acts as an external reinforcement, redistributing the load and reducing stress on the damaged section. Cable bracing is often used as a temporary measure until the pole can be fully repaired or replaced. The third major reason for cable bracing is increased safety and reliability in certain high-risk areas. In these areas, cable bracing is used as a proactive measure to improve the overall robustness of the power distribution system. High-risk areas include locations along major highways, areas with frequent storms, and areas with critical infrastructure. Along major highways, the risk of vehicle collisions with poles is higher due to increased traffic volume and speed. Cable bracing can help prevent pole failures in the event of a collision, reducing the risk of downed power lines and traffic accidents. In areas with frequent storms, cable bracing can provide extra protection against wind and ice damage. This is particularly important in regions prone to hurricanes, tornadoes, and severe winter storms. Cable bracing can help keep the power on during these events, minimizing disruptions to essential services. Areas with critical infrastructure, such as hospitals, emergency services, and communication centers, require a highly reliable power supply. Cable bracing can help ensure that the power stays on during emergencies, preventing disruptions to these vital services. The specific design and installation of cable bracing systems depend on several factors, including the type of pole, the expected loads, and the site conditions. Common types of cable bracing include down guys, side guys, and span guys. Down guys are cables that run from the pole to an anchor in the ground. They are used to counteract the lateral force of conductors and equipment. Side guys are similar to down guys but are installed at an angle to the pole. They are used to provide additional support against wind loads or to stabilize poles on slopes. Span guys are cables that run between two poles. They are used to provide additional support to poles that are located close together or that are subjected to high lateral loads. The installation of cable bracing must be done carefully and according to industry standards. The anchor must be securely embedded in the ground to provide adequate holding power. The cables must be properly tensioned to distribute the load evenly. The hardware must be corrosion resistant to ensure long-term reliability. Regular inspections of cable bracing systems are essential to identify any signs of damage or deterioration. Cables should be checked for fraying, corrosion, and looseness. Anchors should be inspected for movement or corrosion. Hardware should be inspected for cracks or breaks. Any problems should be corrected promptly to maintain the effectiveness of the bracing system. In addition to the specific scenarios mentioned above, cable bracing may also be required in other situations where pole stability is a concern. For example, cable bracing may be used to stabilize poles during construction or maintenance activities. It may also be used to support poles that are located near excavations or other potential hazards. The decision to install cable bracing should be based on a thorough engineering analysis of the pole and its surroundings. The analysis should consider all relevant factors, including the type of pole, the expected loads, the soil conditions, and the proximity to other structures. A qualified engineer should be consulted to ensure that the cable bracing system is properly designed and installed. Furthermore, the National Electrical Safety Code, or NESC, provides guidelines for the design, installation, and maintenance of overhead electric supply and communication lines, including requirements for pole strength and stability. The NESC specifies minimum safety factors for poles under various loading conditions and provides detailed requirements for cable bracing systems. Compliance with the NESC is essential to ensure the safety and reliability of power distribution systems. In summary, cable bracing is an important tool for ensuring the stability and reliability of utility poles. It is required when poles cannot withstand lateral loads, are damaged or weakened, or to improve safety and reliability in high-risk areas. Proper design, installation, and maintenance of cable bracing systems are essential to ensure their effectiveness. By understanding the principles of cable bracing and following industry best practices, utility companies can minimize the risk of pole failures and maintain a safe and reliable power supply. Considerations beyond these specific scenarios also warrant evaluation. For example, changes in environmental regulations may necessitate cable bracing. If new regulations impose stricter requirements for pole strength or stability, existing poles may need to be reinforced with cable bracing to comply. Similarly, changes in land use patterns can affect the need for cable bracing. If new buildings or infrastructure are constructed near existing poles, the wind loading or other environmental factors may change, requiring additional support. Community concerns can also drive the need for cable bracing. If residents express concerns about the safety or appearance of poles, utility companies may choose to install cable bracing as a proactive measure to address those concerns. Economic factors also play a role in the decision to install cable bracing. While cable bracing adds to the initial cost of pole installation, it can also reduce long-term maintenance costs by preventing pole failures. In some cases, cable bracing may be a more cost-effective solution than replacing poles entirely. Technological advancements are also influencing the design and use of cable bracing. New materials such as composite cables and high-strength anchors are making cable bracing systems more durable and effective. Advanced monitoring systems are also being developed to detect early signs of pole damage or instability, allowing for timely intervention and preventing costly failures. The aging infrastructure of many power distribution systems is also a major factor driving the need for cable bracing. Many poles were installed decades ago and are now nearing the end of their service life. These older poles may be more susceptible to damage and failure, requiring cable bracing to extend their lifespan. Furthermore, the increasing demand for electricity is placing greater stress on power distribution systems. As more homes and businesses connect to the grid, the load on poles and conductors increases, making cable bracing more important than ever. The increasing frequency and severity of extreme weather events such as hurricanes, tornadoes, and ice storms are also driving the need for cable bracing. These events can subject poles to unprecedented loads, increasing the risk of failure. Cable bracing can help mitigate the impact of these events and keep the power on for critical services. In addition to cable bracing, other methods can be used to reinforce utility poles, such as pole banding, pole encapsulation, and pole replacement. Pole banding involves wrapping the pole with steel or composite bands to increase its strength. Pole encapsulation involves encasing the base of the pole in concrete or other materials to protect it from rot and corrosion. Pole replacement is the most drastic measure, but it is often necessary for severely damaged or weakened poles. The choice of reinforcement method depends on the specific circumstances, including the type of pole, the extent of the damage, and the budget. In conclusion, cable bracing is a versatile and effective tool for ensuring the stability and reliability of utility poles. It is required in a variety of situations, from preventing failures due to high winds and ice loads to reinforcing damaged poles and improving safety in high-risk areas. By considering all relevant factors and following industry best practices, utility companies can make informed decisions about when and where to use cable bracing to maintain a safe and reliable power supply. The engineering analysis to determine the necessity of cable bracing involves several steps. Firstly, a thorough site assessment is conducted to gather information about the pole and its surroundings. This includes inspecting the pole for any signs of damage or deterioration, assessing the soil conditions, and identifying any nearby structures or hazards. Secondly, a load analysis is performed to determine the forces acting on the pole. This includes calculating the wind load, ice load, conductor tension, and any other relevant loads. The load analysis should be based on industry standards and local building codes. Thirdly, a structural analysis is conducted to determine whether the pole can withstand the applied loads. This involves using engineering principles to calculate the stresses and strains in the pole. If the structural analysis indicates that the pole is overstressed, cable bracing or other reinforcement methods are necessary. Fourthly, the design of the cable bracing system is determined. This includes selecting the appropriate type of cable, anchor, and hardware, as well as determining the optimal placement and tension of the cables. The design should be based on engineering principles and industry best practices. Fifthly, the installation of the cable bracing system is carried out. This should be done by qualified personnel according to the design specifications. Finally, regular inspections are performed to ensure that the cable bracing system is functioning properly. This includes checking the cables for fraying, corrosion, and looseness, as well as inspecting the anchors for movement or corrosion. The inspection schedule should be based on the environmental conditions and the expected lifespan of the system. Furthermore, it is also crucial to consider the aesthetic impact of cable bracing. While functionality is the primary concern, the appearance of the bracing can also be a factor, especially in residential areas. Utility companies may work with communities to find bracing solutions that are both effective and visually appealing. This might involve using different types of cables or anchors, or painting the bracing to blend in with the surroundings. Environmental considerations are also important. When installing cable bracing, care should be taken to minimize disturbance to the surrounding environment. This might involve using low-impact installation techniques or avoiding sensitive areas. Additionally, the materials used in the cable bracing system should be environmentally friendly and recyclable. The cost of cable bracing is another important factor to consider. The cost can vary depending on the type of bracing, the location, and the complexity of the installation. Utility companies must weigh the cost of cable bracing against the benefits of improved pole stability and reliability. In some cases, it may be more cost-effective to replace the pole entirely rather than install cable bracing. Moreover, the legal and regulatory requirements for cable bracing must be followed. These requirements can vary depending on the jurisdiction and the type of pole. Utility companies must ensure that their cable bracing practices comply with all applicable laws and regulations. This includes obtaining any necessary permits and following safety standards. In addition to the technical aspects of cable bracing, communication with stakeholders is also important. Utility companies should communicate with customers, communities, and other stakeholders about their cable bracing plans. This helps to build trust and ensure that everyone is aware of the reasons for the bracing and the potential impacts. Finally, ongoing research and development are essential to improve cable bracing technologies and practices. This includes developing new materials, improving installation techniques, and creating better monitoring systems. By investing in research and development, utility companies can continue to enhance the safety, reliability, and cost-effectiveness of their power distribution systems.